So using just the plain work energy theorem, I know that initial kinetic energy plus the work done by all forces equals the final kinetic energy. Now we saw that, what could I mean by the plain work energy theorem? I mean without using the idea of potential energy. So I've got three forces here that do work: friction, gravity, and the spring. So writing those out, this is kinetic energy initial plus the work done by gravity plus the work done by the spring plus the work done by friction equals the final kinetic energy. And I have expressions for all of those things. I just found them in the previous work. The work done by gravity was mgl sine theta. Let me make that a little bit neater at the cost of making my columns not line up like they should. The work done by the spring was 1/2 kd squared, and the work done by friction was minus mu mg L cosine theta, and that equals 1/2 mv final squared. I'll just move this over. Keep my columns nice and neat for the people looking at these slides later. So this is initial velocity, but the initial velocity is 0 because we're starting from rest. So that means that I can solve for Vf, and that gives me Vf is the square root of two GL sine theta plus k over m d squared minus 2 mu g L cosine theta. So this is doing this problem. Notice I never said potential energy anywhere. Now I'm going to do this problem thinking about potential energy. We'll get the same terms. I'm even going to color code them in the same way, but I'm framing the problem in a different way. So now I'm going to be thinking about as many forces as I can as associated with a potential energy. But I can only do that for conservative forces. Forces that are not conservative, I still have to calculate the work that they do in kind of the same way that I have been doing. So here, the conservative forces that I have that are associated with the potential energy are gravity and the spring force, and the non-conservative forces are friction. So what I'm going to have is initial kinetic energy plus gravitational potential energy plus elastic potential energy. Now, I've still got the work done by friction, because I can't associate that with the potential energy because it's non-conservative, equals final kinetic energy plus those forms of potential energy. Should probably label these final and initial, right? Kayla, did you have a question? Yes, PE elastic is the potential energy of the spring. Whoops, I messed up. This should say initial. That should say initial. So now all I have to do is put in what these terms are. So in the end, I am at the ground. So the final gravitational potential energy is 0. Also, the final elastic potential energy is 0 because the spring has been released. So now if I put in what these things are, oops. Oh, likewise, the initial kinetic energy is 0 because we're starting from rest. So now let's put in what these things are. I have mgy initial. Well, we'll go ahead and write it out. Mg L sine theta that's my initial height, plus 1/2 kd squared, that's the initial compression. I still have the same term from the work done by friction. Equals the final kinetic energy. Your bunny raised its hand. Okay, I demand a picture of your bunny. That sounds absolutely adorable. Yes, Renji, exactly. Potential energy is just the potential of a force to do work. So it shouldn't surprise us that we get the exact same terms in the exact same equation. So let's even make a note of this. And then solving this for v sub f, I get the same thing. Plus k over m d squared minus 2 mu g L cosine theta. So I've gotten a lot of questions from students about like how do I know when to use potential energy? How do I know when to use the work energy theorem, when to use potential energy? As you see here, it comes out the same either way. James asked, why is the normal force using cosine rather than sine? Let me get just a blank page here to do that. So if I zoom in on this and we draw a force diagram, here's the normal force. Here's gravity. And the components of gravity are these. Remember when we did this in Unit 2? and this angle here is the same as this angle down here. So we know that the thing doesn't go up and down the ramp. So this component here is mg cosine theta, and that's got to be equal and opposite to the normal force. So the normal force is mg cosine theta just because the motion that way is 0. Martina asks, does it matter which equation you use? No, it doesn't. Again, with each force, you can either think of it as associated with a potential energy, or you could just think about how much work it does. Grace asks, can you use the conservation of energy equation even if energy isn't conserved, as long as you take non-conservative forces into account? Yes, because after all, this thing with potential energy, this equation up here, whoa, that wasn't what I wanted to do. This equation here just comes from the work-energy theorem. Really, a non-conservative force is just one that turns energy into a form we can't account for. Like friction, friction turns kinetic energy into heat. And we haven't studied heat yet in this class. So when we say non-conservative force, really all we mean is that is a force that takes energy away from mechanical types of potential energy that we know how to calculate and turns it into other kinds of energy like heat and light that we don't have a way to solve in mechanics. Grace, does that help? Jason asks, what's K over M? In order to solve for V final down here, I had to divide both sides of this equation by 1/2 m. So this K over M here, this term, like look on the left, I'm about to draw an arrow, this term is the same as that one divided by 1/2 m. Okay, I'd like to move on to our new idea, which is power. No worries, Jason. I cannot follow other people's algebra. Like, I took a mathematics class when I was a PhD student. It was a fascinating topic in perturbation theory and mathematics, and it was fascinating, but I only learned like 10% of the stuff because everybody else in the class was just so much better at doing algebra than me. They'd be like 10 steps ahead of me all the time, and I'd have to like go home and think about all the algebra super carefully. So I cannot follow other people's algebra. So no shame there. Okay, new topic, power. I'm a little crunched for time, so I'm going to go a little bit rapidly, but again, ask questions if you've got them. This will show up again on the homework. So power is a rate of doing work or transforming energy. I might say, for instance, that if something does 1,000 joules of work in 10 seconds, that it's doing work at a rate of 100 joules per second or 100 watts. So the units for this are joules per second, which are called watts. And this is a super important thing in engineering because we have a lot of machines that are limited by the rate at which they can do work or the rate at which they can transform energy. So right now my laptop is, it's getting close to its maximum of 25 watts. So it's converting about 25 watts of electric potential energy into heat every second. Excuse me, 25 joules of electric potential energy into heat and light every second. But if we think about things doing mechanical work, these vary from, birds actually have a surprisingly high sustained power output. That's how they can fly. A person on a bike is a couple hundred watts. We're going to do a person on a bike example. A horsepower is 750 watts. That's what you can get out of a horse averaged over a working day. But you can get a lot more than that for a moment. Automobile engines range from 100 horsepower or 75 kilowatts up to 400 or even more kilowatts. And as we go up to bigger and bigger things, A nuclear reactor like the one at the ones that power us near Lake Oneida may be producing over 1 billion watts of electricity. Um, so what I'd like to do now is to look at power in the context of mechanics, because this is what comes up in engineering. So we want to know the rate at which a force does work on an object moving at some speed. And, since I put a vector sign on that, I really ought to say velocity, right? So we'll start with the work energy theorem, like we always do. If work is force dot displacement, and I want to know the rate at which work is being done, I take time derivatives of both sides. So take the time derivative of the left-hand side, take the time derivative of the right-hand side. Force is constant, so what's changing over time is displacement. So what is the time derivative of work called? Somebody type in chat. Yeah, exactly. The rate at which work is being done, this is just power. What about the time derivative of displacement? Velocity. Yep. So another way to say this is that power is dot product of force with velocity. This is the new principle from this unit that you will need. So in our remaining 7.5 minutes, I'd like to apply this to 2 examples.